Well, good evening. Welcome to Space Oddities. Thank you for being with us on this Tuesday night. Hope you're okay. Hope you've all had a fantastic week. And for those of you in the UK, I hope your weather hasn't been too cold and too snowy and hasn't disrupted your lives too much. Although, to be honest, here in Spain, it's been really cold. I actually had to put a jumper on to go out today. So it's been absolutely freezing. So anyway, like to say, first of all, thank you, Gerard, for your kind donation, sir. Thank you so much. Hi, Jerry. Hi, Sandra. Hi, Stuart. Hello, everybody. Derek. And good to have you with us again. So what have we got for you this week? Well, this week we have Dr. Lou Mayo here. Is going to talk us through the latest NASA images of 3I Atlas. And I'm sure he's going to dispel a lot of the idiocy that's being talked about these images. So we live in hope. Also like to welcome back Dave. How are you, Dave?
Good, thanks. Thank you.
Good. And Dave will be doing another On This Day a bit later on this evening. And we've officially appointed Dave our historian for Space Oddities. So he is the man who knows. So we'll look forward to that later. Roger's here. How are you, Roger?
Good evening. I'm fine.
Good to see you. And Michael's here. He's working on his impression of Brains from Thunderbirds, as you can see.
Hey.
So that's good. And of course, I'm here as well. It'd be funny if I wasn't. I'm real. I'm not an AI generation. So there we are. Anyway, let's get on with things. So let's just go through the normal housekeeping stuff. First of all, thank you all for being here. And we were just talking about Christmas, actually. And on the 23rd of December, which is 2 days before Christmas, believe it or not, Tuesday the 23rd, we're going to do a Christmas quiz for you. We haven't done a quiz in a while, so we thought we'd do a nice Christmas astronomy quiz for you. So you'll have that to look forward to. Don't forget that at some point in January, which we haven't yet confirmed, we'll be having Dr. Alan Stern as a special guest on Space Oddities, who is, as you may remember, or you may know, the man who basically pushed through the New Horizons mission to Pluto and made it happen. And under extreme pressure and against all odds, he made that mission happen. If you haven't read his book, then it's a fantastic read. So we got that to look forward to in January, and no doubt some other good stuff as well. If you would like to support Space Oddities, then the most obvious way of doing so is to actually buy us a coffee. And you can click this link or click the link in the chat, or you can scan this QR code on the screen. This will take you to the Buy Me a Coffee page where you can keep us going in caffeine, and that is much appreciated. You can also go, of course, to the Space Oddities shop, where you will find the Space Oddities t-shirts, which, let's be honest, you're probably not thinking about buying at the moment, but also wonderfully warm, beautifully warm Space Oddities hoodies for the winter. So you can go to the Space Oddities shop and buy those there as well. We still hope to expand our line of merchandise. We've been saying we're going to do this for a while, so we'll give that some serious thought and offer you some more lovely merch to brighten your days. So there we are. Thank you so much for your donations. If you would like to make a donation directly to Space Oddities, you can click the icon with the $ under the chat window, and you can make a donation to us directly. And every bit of money helps us to help you, really, to keep you going with incredible science, factual science, and the quality stuff which I hope we bring to you. And every bit of money goes to keeping us going, basically. So none of us are stashing lots of cash in our pockets, maybe one day, but not at the moment. So we're going to move on now. And actually, the first thing we're going to do this evening is go to Lou, and going to tell us about these latest images of 3I Atlas. So let me just get that up for you, Lou. And here we are.
Thank you, sir. Well, it is what everyone who is anyone is talking about. It is the topic of the month, perhaps the topic of the year, Comet 3I Atlas. Alien spacecraft from outer space, possibly, or just another damn comet. We don't know. But we're going to find out today.
Today.
So
That's exciting.
right now,
Right now.
you know, the wait is over. So perhaps you have seen some headlines like this. And what's interesting is no one is saying anything specific. So this top on the right says, do NASA's 3I Atlas photos show evidence of spacecraft targeting meteors in its path? Harvard scientist speaks out. On the lower left, a strange object has entered our solar system, and one scientist says it might be an alien spacecraft. It doesn't mention one scientist on drugs, but go ahead.
Can I have a fairly substantial bet as to who that scientist is?
Go for it. I don't know.
It's got to be Avi Loeb.
Oh, perhaps.
Perhaps, he says.
All right. Okay. I can neither confirm nor deny that. That's how we talk in the United States now. I can neither confirm nor deny that. But I did find 9 reasons this scientist is suspicious the object screaming past the sun is a city-sized alien spacecraft. Wow. And I won't go into those 9 reasons because they're not important, because none of this is true. There is absolutely no reason to suspect this is anything but a natural small body, as we call them at NASA. And we'll be going over some of the evidence for that.
There was actually a YouTube video I saw yesterday. I didn't watch it. I just saw the title that says 3I Atlas is millions of times bigger than NASA are saying, says scientist.
Millions. Wow.
Million.
I didn't know. I don't have a slide on that. I'm sorry. But as I tell my students here at Marymount, if they remember nothing else from my astronomy class, I want them to remember the words of Carl Sagan: incredible claims require incredible evidence. So let's move on from this clap track and let's get into the data. First of all, as you might have guessed from its name, 3I Atlas was discovered by ATLAS, the Asteroid Terrestrial Impact Last Alert System. ATLAS is an asteroid impact early warning system developed by the University of Hawaii. It's funded by NASA. It consists of 4 telescopes. There are 2 in Hawaii, 1 in Chile, 1 in South Africa. They automatically scan the whole sky several times every night looking for anything moving. The ATLAS system combines a comparatively small telescope with a very powerful camera. It's an equatorial mounted 50 centimeter diameter, so that's about 20 inches for the US contingent. It's an F2 system, optical system with a 110 megapixel CCD array. You know, I'm pretty sure my Samsung cell phone has a 200 megapixel camera, so I don't want to make too much out of this. Nevertheless, a major feature of the telescope is it has a very large field of view, about 7.5 degrees. So that's about 15 times the diameter of the full moon. So with a system like this, the whole night sky visible from Hawaii can be imaged with about 700 separate telescope pointings. And it takes about 30 seconds for an exposure and 5 seconds to read it out. So each telescope can scan about 25% of the sky 4 times a night. So you can image the whole sky twice. ATLAS will provide some warning time for dangerous near-Earth asteroids and comets. Larger asteroids can be detected further from Earth. Smaller, like 20-meter or so asteroids can be detected several days out. 100-meter asteroids weeks out. And a 100-meter asteroid has about something like 10 times the destructive force of the 2021 Tonga volcanic eruption. So basically, we're pretty much screwed, guys. Enjoy life while you can. That's what I say. So its detection on July 1st of this year, the ATLAS telescope in Chile first reported observations of a comet originating from interstellar space. and arriving from the direction of the constellation Sagittarius. This interstellar comet the 3 is for the third interstellar comet that we have detected. I is for interstellar, and then Atlas for the system that discovered it. You always name comets after their discoverer, and in this case, it was an automated. It's currently or 670 million kilometers away. So, you know, you might think this is strange. Some interstellar interloper. I made that up on the spur of the moment. Coming into our solar system, but the formation and evolution of our solar system, of solar systems in general, of small bodies and planetary systems, predict that they could escape into interstellar space at any time as a function of gravitational interactions with their planetary bodies. So we've characterized 2 so far. One was called 1I, and now you know why 1I. 2017 U1 Oumuamua, and the other is 2I Borisov. And frankly, by observing these comets, there were more questions raised than answered. So it's important to assess and to study 3I Atlas to broaden our understanding of this complex topic. And I think I failed to mention that the images that you're seeing here are the original images taken from the Atlas telescope in Chile. Okay. Here is this diagram is the trajectory of 3I Atlas as it passes through the solar system. It made its sun in October. Just to while at rest, this comet poses no threat to Earth, and it will remain at a distance of about 1.6 astronomical units, 150 million miles, 240 million kilometers from Earth. 3I Atlas is in the constellation Virgo and moving away from the sun, with its speed decreasing from its peak velocity. And that's exactly what you'd expect from Newton and Kepler celestial mechanics. It's approximately 300 million kilometers from Earth now, and will have its closest approach to Earth on December 19th of 2025 at a distance of about 270 million kilometers. Current speed, 244,000 kilometers per hour, but it will continue to slow down as it moves away from the sun and experiences less and less of the sun's gravity. And this is exactly what you'd expect from a natural object. Here in this image, a team of scientists used the TTT3, the 2-meter twin telescope, to image 3I Atlas from July 2nd through July 3rd, scaling the extent of the object. So you can see a few scales here. These white lines are about 22 to 25,000 kilometers in size. Now, combining this with HST data, the size of 3I Atlas, 320 meters on the low end and 5.6 kilometers on the high end. Now, that's a big range, but the size estimates are based in part on an estimated albedo or reflection constant of the comet. So depending upon the material that's reflecting the light, that would increase or decrease the estimated range. So back in early July, the best images we were getting of 3I Atlas looked like the image that you see right here, kind of faint, kind of blurry, views of what appeared to be not much more than a point-like object, but rather an source surrounded by a halo-like appearance. And so one of the challenges is, where does the comet end? In an image like this, where does the comet end and the halo begin? With a source like this, you can still measure the object's velocity and position very well. That's not a problem. And that enables you to determine its orbital trajectory, both past and present, including pretty accurate determination of its origin. But its size cannot be well determined, as there are no observed delineations between the central nucleus and the diffuse coma in this image. So let's look at some more images that have been released by NASA recently. This is the high-resolution imaging science experiment called HiRISE aboard, it's a camera aboard the Mars Reconnaissance Orbiter, MRO, orbiting spacecraft. Captured this image of 3I Atlas on October 2nd, and at that time the comet was about 0.2 AU from the spacecraft. You guys all know AU? Can we say AU?
Yes.
19 million miles, 30 million kilometers. This multi-frame animation shows interstellar Comet 3I Atlas as it moves across a field of stars, and this was taken by the Hubble Space Telescope, probably the WIFPIC 2 Wide Field Planetary Camera 2 image on July 21st. That's pretty cool. NASA released this GIF of Comet 3I Atlas captured by the Punch mission between September 28th and October 10th. Punch is a heliophysics mission. The comet is a white dot at the center, and the bright blob that keeps flashing past is the planet Mars. Punch, yeah, cool stuff. Punch is NASA's, get this, polarimeter to unify the corona and heliosphere mission. People stay up late at night coming up with these acronyms. It's a four satellite mission designed to observe the sun's outer atmosphere and the solar wind in 3 dimensions. Punch observations reveal the comet's tail, which you can see kind of angling out towards the lower right. And it's visible as kind of this very, very slight elongation. So this image shows the halo of gas and dust, or in other words, the coma surrounding 3I Atlas. It was taken on October 9th, 2025 by an instrument aboard NASA's Mars Atmosphere and Volatile Evolution spacecraft, MAVEN, which has been studying Mars from orbit since 2014. MAVEN was launched to find out why Mars' atmosphere is eroding, and it figured out that the solar wind is pretty much knocking the heck out of the atmosphere, and has been doing so for billions of years. The instrument, the imaging ultraviolet spectrograph, takes pictures of the ultraviolet part of the spectrum to reveal the chemical composition of objects. The center of the image has the brightest pixels, indicating where the comet is. The next brightest shades in the image indicate areas where the instruments detected atoms of hydrogen coming from the comet. This hydrogen is released when sunlight heats the comet, causing its water to sublime, in other words, turn directly from ice into, and once released into space, the water molecules break apart into oxygen and hydrogen atoms. You're going to know everything you need to know about Comet Atlas right here today. Well, here's a fun graphic. This is also ultraviolet composite image of 3I Atlas, showing the hydrogen atoms that are escaping from the comet. So here you can see interplanetary hydrogen. You can see hydrogen escaping from Mars in this image. And then you can also see the hydrogen emission from Comet 3I Atlas. This hydrogen emission comes primarily from water, from the photodisassociation of water. And as we'll see in some subsequent slides, there's a fair amount of water ice in the comet. All right, here's a high-rise image. This is an annotated image of 3I Atlas captured by Mars Reconnaissance Orbiter. And it shows the general trajectory indicated by the arrow of the comet, and captured by the high-rise imager on MRO. Let's see, I think this is supposed to play. Let's try this out. There we go. Oh, I guess do I have to keep clicking this? Oh, for God's sake.
Yeah, probably.
All right. Well, anyhow, this is a kind of a fuzzy image of the comet traveling through the solar system at about 130,000 miles or 209,000 kilometers per hour. This was made visible using a series of stacked images. Whoops, let's go back. Using a series of stacked images from September 11th through the 25th, using the heliocentric imager on the Stereo A spacecraft. Stereo was one of 2 spacecraft launched to get full coverage of the sun. But here we're using it to see Comet 3I Atlas. Originally, the comet was expected to be too faint to be observed by this instrument, but the comet brightened enough to be visible, allowing the instrument to see the comet against noise dominating the background through a combination of frames. We'll play this one more time if we can. Let's see. There we go. Okay. This image, the NASA Psyche mission acquired 4 observations of interstellar comet 3I Atlas over a course of 8 hours on September 8th and 9th, when the comet was about 33 million miles from the spacecraft. The data captured by Psyche's multispectral imager is helping astronomers both refine the trajectory and learn more about the faint coma or cloud of gas surrounding the nucleus. Now, Psyche is a spacecraft that was launched. It's part of the NASA's planetary science program, and it was launched to an asteroid that is believed to have very high metal content and believed to be the core of a planetesimal that didn't quite make it into full planethood. So that will be interesting finding on its own. Three I Atlas was also observed by the SOHO mission, the Solar and Heliospheric Observatory. This faint image of the comet, as observed by SOHO, was taken between October 15th and 26th. The comet appears as a slight brightening in the center. Let's see, do I want to say any more about this? I will say that SOHO has become perhaps the most prolific comet hunter of all time. With the help of a citizen scientist program called Sungrazer, SOHO's imagery has led to the discovery of more than half of all known comets. So in other words, over 5,186, at least at the time of this writing. So this is not the only SOHO has imaged. All right, let's get down in some really hard data here. Okay, this is a spectrum from the James Webb Space Telescope NIRSPEC spectrometer. NIRSPEC is the near infrared spectrometer. It's a prism spectrometer on board JWST. Here the sky background has been subtracted out, and you can see the spectrum plotted with a logarithmic flux scale on the y-axis here, and wavelength in microns on the x-axis. These features relate to water. You can see clearly identified carbon dioxide and carbon monoxide, and they're all labeled here. The water exists in the icy phase only, and carbon dioxide as a gas that's emitted with pretty strong signature. Even a small CO carbon monoxide feature is present. What is specifically remarkable about this spectrum of 3I Atlas could be that its water ice to carbon dioxide ratio has a large excess of CO2 compared to the amount of water present, suggesting that, from what we understand of comets, suggesting that perhaps this object either had an unusual origin in terms of its composition for, say, a Kuiper belt object, or that it's more differentiated in terms of composition than a standard Kuiper belt object. And by differentiated, I mean that it's had time for the materials, the heavier materials, to settle toward the center, the lighter materials toward the surface, and so it's stratified, and so we're not seeing the whole bulk combination of the comet. Only a small amount of carbon monoxide is present, as indicated, and this could be the result of billions of years of evolution and travel through the interstellar medium. And I've saved the best for last. Well, I mean, if you're a nerdy scientist, this is the best for last. If you're not, forget it. This is a reflectance spectrum of 3I Atlas with 3 different colored templates of S, D, and Z type asteroids shown. Shaded areas indicate the standard deviations of the template spectra. Simultaneous observations were performed with spectrophotometry with a 3I Atlas from data taken from the tricolor CMOS camera and spectrograph on the SUIMI, which I think is a Japanese telescope, 3.8 meter telescope, on July 15th. Okay, These light curves show no significant variation during the 2.3-hour observation, which probably is suggestive of a very slow rotation of the object and is in good agreement with previous studies. But here's the kicker. Visible color indices suggest it has a red surface very similar or slightly redder than that of D-type asteroids. So perhaps 3I Atlas is not a comet after all. Perhaps it is more akin to an asteroid. And I will leave you with that disturbing thought that's going to keep you from sleeping all night. But that's the way it is, guys.
Okay, thanks, Lou. So, I mean, it's a comet-like object, yes.
Well, we know in our solar system, we say we have comets and we have asteroids, okay?
Yeah.
And we say that comets form outside the freeze line and asteroids form inside the freeze line. And there are a couple of freeze lines for water ice and CO2 ice. But in fact, it's kind of a continuum, right? And so you could have like comet-like asteroids or asteroid-like comets, I guess, with different abundances and ratios of water to CO2. So maybe that's not so unusual. Dave, you're more of a surfaces guy than I am. I hate surfaces. I only love exciting atmospheres. So perhaps you have some thoughts on this.
Well, at least the influence of the surface on the atmosphere must be important to you. But in any case, no, you're right, Lou. I mean, there is.
Of course, I'm right. That's not the point.
Of course,
okay.
of course.
But go ahead, please, Dave. Please share with us.
Correct. Yes. Well, in any case, no. This continuum of the spectrum of it's true. I mean, an asteroid could have a lot of volatiles, a lot of stuff that will basically get heated up and come off as gases and look like a comet or a comet. I mean, a lot of comets have been around the sun so many times that they've basically burned off everything that's that you'd be able to see. In other words, all the ices and all the water has already been kind of cooked out of them, and they're just going around, and they look like an asteroid. So yeah, you're right. And then it's further complicated by the fact now it's an interstellar object. At least with a comet or an asteroid, we can kind of work back to figure out what their original orbit was around the sun. But this, we have no clue. I mean, this was around some other star. It came, for whatever reason, who knows why, came shooting out into interstellar space and then ended up in going through our solar system. And who knows what its original orbit was? There's absolutely no way to work back to that. So yes, it's in a way it's almost just semantics, right? A comet or an asteroid when you get to these kind of areas, things in the gray area. So yeah, you're right.
I see we're letting cats in now. Okay.
Yeah. Sorry about that. Okay. So yeah, I mean, I can't remember the name of the object in the solar system that most of the time is an asteroid, but it does develop a cometary-like tail in some part of its orbit. I can't remember the name of it. So this distinction between comets and asteroids is not clear cut. We don't.
Centaurs are you talking about, Andy?
Yes. Yeah. There's one in particular that I can't remember which one, but it develops quite a noticeable cometary tail. So as you said, it's a continuum, isn't it? And we don't know exactly why this happens, or the composition of those objects makes it happen. But as far what intrigues me. What puzzles me about 3I Atlas is that we had Oumuamua, which we observed far too late to really get any decent data from. But then people immediately started saying, "Oh, it was an alien spaceship," and blah 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 blah. So that was our first interstellar visitor that we know of. Obviously, there'd been many more in the past, but the first we've observed, caught in the act. But then we had 2I Borisov, which nobody said a word about. Nobody, as far as I saw, had suggested, "Oh my God, it's an alien spaceship." And then we get 3i Atlas, and everybody goes absolutely hysterical over it being an alien spacecraft. So, you know, I'm just wondering why didn't they do the same with 2i Borisov? And I think one of the reasons is that we had very good images of Borisov that you could see at a glance was without doubt a comet. It looked very much like comets in our own solar system, although it did have a very different sort of carbon dioxide to water ratio than 3i Atlas. But nobody said a word about Borisov, and all I can think about this is that if Avi Loeb hadn't started saying that it was 3i Atlas is an alien spacecraft, nobody would have said a word about it apart from astronomers. And I think he's got a lot to answer for, to be quite honest, because it is getting absolutely hysterical on the internet about this comet.
I think it's important to know what our alien overlords think.
Yeah, yeah,
we need to find out.
Yeah. Yeah, I mean, it's got all of the physical characteristics of a comet. It's exactly what you would expect a comet to look like. The chemical composition is obviously different to solar system comets, but it comes from another star system. It was born, 7.6 billion years ago, according to estimates, in another star system in a very different environment, probably out beyond the frost line of carbon dioxide. So, we would expect it to be different. And indeed, it would have been absolutely astounding if this comet had not been different to solar comets. We should look at it like that. Of course, we're going to have questions about it. Of course, there are going to be things that are different and odd and strange about it because we've not seen them before. But the internet has gone hysterically crazy over it being alien spacecraft with absolutely no justification. So I think it's sad that when people, could have been marveling at this interstellar visitor and saying how lucky we are to see it and wanting to learn about it. No, let's not do that. Let's say it's alien spacecraft. The most ridiculous one this week has been that it's part of Project Bluebeam. I don't know whether you've heard of Project Bluebeam. No, well, this is a going around the internet like crazy. It's the idea that NASA are planning to fake the second coming of Christ.
Well, that I could believe.
Yeah. Honestly,
I thought you were going to say some kind of loony thing, but no.
How did they even find out about that, Lou? I thought we were keeping that a good secret.
Yeah.
I can't.
I just said I could believe it. I didn't confirm or deny its existence.
Yeah. Can I just reply to Rupert Fellows here, who says, "Can you prove it isn't an alien spacecraft?" Rupert, we should always keep our minds open to that possibility. Nobody's saying it's definitely not an alien spacecraft. All we can go on is the data and the observations, and the observations demonstrate conclusively that it's a comet. There's no other reason for thinking that it's an alien spacecraft. Every single so-called anomaly that's been going around social media, most of them are just nonsense. We
also, maybe we could actually, but I'm not sure if we could prove that it's not an ice cream sundae. Can we?
No.
I mean, it has water ice in it.
Yeah. True.
Large, for like the kind of. And Rupert, nobody's mocking the scientific method. You're obviously new here. We are very, very, very much scientists here, and we thoroughly support the scientific method. But it's not scientific to say that this is an alien spacecraft based on absolutely no evidence whatsoever. So there we are. That's it. That's how the scientific method works. You can only go on the observations, and the observations indicate that it's a comet. So end of story. One other thing I'd like to bring up, Dave, you mentioned correctly, we don't really know where it came from, but assuming it came from a solar system at some level of formation, we also don't know how many trips around its star it made.
Right.
And what its perihelion. No, you don't call it perihelion, you call it Stella or something.
Peristellium? Yeah, that's good. Well, I don't know.
So how many opportunities?
Periapsis, anyway. Periapsis.
Periapsis.
General
Thank
enough,
you.
right? You can
Thank
do
you,
that
sir.
for anything. Yep.
Hmm.
So
No,
many
that's a good
times
point.
it
And I
had
was
to strip gases off of it.
I was right. I didn't know how much you wanted to get into this whole thing, but yes, no, that's exactly true. I was thinking that when you were talking about it, we have no idea of its history. Comet Halley comes around every however many years, and Comet Encke comes around like a lot, and it's getting, every time it comes by the sun, it's getting more and more of its volatiles burned off. So we have no idea of the history of this thing, asteroid, comet, whatever you want to call it, from another solar system, which almost certainly had to have formed around another star. I can't picture any scenario of this thing forming in interstellar space. It doesn't make any sense at all.
No, that
Anything I
does.
understand. So it
And
almost certainly came from some other star.
It's not quite correct to say we don't know where it came from. We don't know where it originated. But
okay, fair enough, right.
Yeah, using Europe's Gaia data, they've tracked its path back 10 million years.
Right.
And it looks like they have identified 62 and possibly 93 stars that it has had encounters with over the last 10 million years. But they can't trace it any further back than that. And this was due to high precision, incredibly high precision data from Gaia. So we know it has had encounters with lots of stars. We don't know how close it came to any of those stars. I mean, without that data, it's pretty meaningless.
It's kind of a loose comet, right?
Yeah, that's right.
There's no ethics or morals, really, as I can tell.
Well, if it came from a constellation with more than 2 stars, then it's going to be difficult, right?
Right. Michael will enlighten us.
Thank
Hey,
you.
Elena, I think the name might be Elena, gave us the word periastrum.
Yes.
Thank you,
Periastrum. Okay.
And you're welcome, Elena.
Thank you, Elena.
Periastrum, yes.
Periastrum. Yeah, sounds like a TV detective. Once it gets closer to the Earth, we'll have more observing opportunities to get more images. And it's also worth pointing out at this juncture, because again, I've seen lots of people completely misunderstanding it on social media. All of the images from spacecraft and from the Mars rovers were taken with cameras that were not really designed to do the job. So people have been expecting glorious high-resolution color images to be looked at by NASA, and a lot of people have been disappointed, saying, "Oh, is that it? That's a terrible image." When you think about, for example, look at the Mars rovers. I mean, look at the aperture of the cameras that they have, tiny.
Right.
And it was a miracle that they got anything at all, to be quite honest. I think it was an amazing feat to pull that off. Also, the Psyche camera and these are not designed to look at faraway objects. They're designed to do planetary work, and in the case of Psyche, asteroid work, to point downwards and not upwards, if you like.
Right. I would get questions like that, about the images that we had at NASA, and about why all sorts of things. Why can't you see stars? Why can't you get a better resolution image? And it's of course the cameras are designed for these planetary missions to look at surfaces. They're not designed for that. And as you said, it's amazing that they could even get the kind of pictures they could with these cameras. It's they're made to look at craters and surface features.
The ones from Mars in particular, they were actually excellent photos, considering that those cameras are just not designed for that sort of work.
Right.
I think they did an amazing job. But once it gets closer to the Earth, we can get the big telescopes on it and get some much better images.
Just use a sea star. That's all you need. That's all you need.
Yeah. Well, perhaps soon they'll bring out a massive sea star to make this sort of work easier. But yeah,
like an S10,000 or something.
Yeah, absolutely. So anyway, so there we are. But we will have to wait and see. I mean, in a few months it'll be gone and it will drop out of public interest, and they'll move on to the next news cycle, and it will be forgotten in no time at all, I'm sure. which is a shame. But you know, Europe have got this idea to send a spacecraft to either L1 or L2 to just sit there and wait. And if another such visitor comes into our solar system, send the spacecraft off to intercept it.
Oof.
Which I think is a, you know, it depends on a lot of things, obviously. But I think it's, you know, it's a good idea, so that we do have something ready to go when we get our next interstellar visitor. It's not a question of if, it's when. So, so you know, so that would be good. Also, Lou mentioned the sort of the planetary defense network. That has demonstrated as well that we severely need to upgrade that. Definitely needs a lot more money putting into spotting these objects, because you know, this comet wasn't dangerous to the Earth. It was never going to come anywhere near the Earth, but we need to spot these objects, you know. And I was reading this week, although I didn't have time to go into it, that there's an asteroid. I shouldn't say this really, it'll be all over social media and it'll be aliens again, but never mind. There's an asteroid that's been detected that is Torino scale 3, which I think is
okay. I heard that either.
yeah, I think it's the first asteroid to be 3 on the Torino scale. So that's, you know, potentially very hazardous. So you know, we need to defend our planet better. Basically.
Yeah, but it's a matter of priorities,
yes.
Andy. Planetary defense on one hand, golden ballrooms on the other. It's hard to know. It's hard to know how to prioritize.
Lou, we're gonna have to leave it to the European Space Agency and some of the other countries, I think, to do this now.
Yeah.
Oh, I hope so.
Yeah. Well, I mean, I'm sorry that it's happened. That, you know, like yourself, Dave, so many people at NASA are losing or have lost their jobs. But it could be Europe's gain, you know. I mean, the ESA could consist in a few years of you know, a lot of ex-NASA scientists, which for Europe will be brilliant, but not good for you, obviously. So come on over to Europe, Dave. It's
my wife and I used to joke about, I should, you know, get a job at ESA and we could live in Europe for a few years and stuff. But ESA has a pretty strict quotas on who they hire. You know, they have quotas from every country, you know, Spain and France and England and Germany. Everyone gets a certain number, and the US isn't in there. So I don't know if I'd be welcome.
Of course you would.
It was a fun idea, though.
You'd always be welcome.
They're welcoming us with open arms now, Dave.
Yeah,
maybe so. Maybe there's a lot of competition though now. I don't know. I'm not the only one, obviously.
Yeah. Yeah.
Anyway.
So there we are.
I'm sorry. Can I just ask one other question, Lou? It's a somewhat related question, and that is that, you know, I know there's Atlas and there's a bunch of these others, you know, automated surveys looking for comets. You know, do you think the days of amateur astronomers discovering comets are over or ending, or do you think there's still a place there?
Oh, Lou's frozen.
I don't know if you...
Does that make sense? Oh, he is. Oh,
there we are.
I shocked him so much with the question.
I don't think so.
Okay. Good.
I think there are perhaps even increasing roles for amateur astronomers with the citizen science programs as partnerships with researchers. But, you know, telescope time is expensive and hard to come by. But if you're an amateur astronomer, if you've got a 10 telescope, 12-inch, whatever you have, and you're retired, what the heck? You have as much time as you want. So I think maybe not.
Yeah.
I think that
we're
still in that era.
And hopefully, you know, after this terrible debacle over 3i Atlas, perhaps it has interested people to find out more about what's in the universe and objects in the solar system and stuff like that. And if it's inspired just one person to become an astronomer after all this, then great, you know. So there we are. All right, then we're going to move on now. Thank you, gentlemen, for that. We're going to move on to have a look at this week's news. So just give me 1 second. I've only got 3 items in the news for you this week, but anyway. So let's just set this up here. But I hope you'll find these interesting. So here we are. So this is the news this week. Hope you can see that. Let me just get rid of all of those. Okay. So what have we got in the news this week? Well, we have, first of all, a really lovely James Webb image. I don't know whether you saw this. It's a new image taken by James Webb. This is the star system called Apep, which is named after the Egyptian god of chaos, believe it or not. Now, this beautiful image reveals 4 concentric spiraling dust shells emanating from a pair of Wolf-Rayet stars, something previously undetected. Earlier observations before the James Webb had only seen 1 shell. If you don't know what a Wolf-Rayet star is, it's a rare, very massive star in an advanced evolutionary stage, characterized by intense stellar winds, prominent broad emission lines of helium, nitrogen and or carbon in its spectrum, and the near complete loss of its outer hydrogen layers. Now, some massive stars go through this so-called Wolf-Rayet phase, but that phase is incredibly short. It only lasts a few 100,000 years, which is nothing in the life of a star, of course. Now, this image shows that the shells expanding outwards over time form during episodic dust production events when the 2 Wolf-Rayet stars approach each other quite closely in their orbit. By combining JWST's high-resolution dust shell mapping with 8 years of data from the VLT in Chile, researchers have refined the orbital characteristics now. The 2 stars complete an orbit approximately every 190 years, with a close pass phase lasting about 25 years, during which all of that dust is produced. The one in the dust in the shells you can see here. But something else has been discovered as a result of these observations. Beyond these 2 Wolf-Rayet stars, the JWST has confirmed that there's a 3rd massive supergiant companion star bound to the system. And this is a simulation of what's happening. So the influence of this 3rd star slices through these dust shells, creating these visible cavities or funnels in each of the shell structure. The dust itself is composed largely of amorphous carbon, which retains heat and radiates it in the mid-infrared, and this is what Webb sees. The shells are expanding at about 2,000 to 3,000 kilometers per second, which obviously is quite a lot. But the significance of this whole system lies in its rarity. While there are a few 100 Wolf-Rayet binaries known in the Milky Way, systems with 2 Wolf-Rayet stars and such a long orbital period are unique. The observations thus provide a valuable testbed for stellar evolution models, particularly for massive stars that may eventually explode as supernovae or produce gamma ray bursts. In other words, JWST has dramatically improved our view of the Apep system, making visible a 4-shell spiral structure and refining our understanding of the star's interactions and dust production dynamics. So this is a big step forward in understanding, firstly, Wolf-Rayet stars, secondly, dust production around such stars, and the unexpected discovery of this 3rd supergiant, which we can't see, presumably because it's shielded by dust, is incredible. And this incredible structure around these 2 Wolf-Rayet stars. So that was quite interesting this week. Now, moving on, there's astronomers using the Webb. Webb's been in the news a lot this week. Believe they may have found evidence of the 1st generation of stars. This generation of stars, the first stars in the universe, have long been sought, but obviously they are incredibly difficult to detect. These are known as population 3 stars, confusingly. You think they'd be population 1, but they are known as population 3 in a distant galaxy designated LAP1b. The light from this galaxy has traveled for about 13 billion years, showing the system as it was about 800 million years after the Big Bang. These primordial stars are theorized to form pristine hydrogen and helium gas, lacking heavy elements, and to be extremely massive. Often these stars were hundreds of times the mass of the sun, and they were very short-lived, of course, because they exploded in just a few million years, we think, in supernovae. But in the JWST data, the stars in lap 1 appear to be embedded in a metal-poor environment. Now, don't forget, when we talk about metals in astronomy, we're talking about any elements that are heavier than hydrogen, helium, and lithium. Don't know why they were called metals. It's a very poor choice of words, in my opinion, but what do I know? But this is a metal-poor environment, and as luck would have it, they were visible because of gravitational lensing. There's an intervening galaxy cluster which magnified these stars beyond it with gravitational lensing hundreds of times, which allowed the JWST to make the observations. If confirmed, and you know that's a big if, that all of this has to be confirmed yet by further observations, it would mark the first direct observation of the universe's earliest stars, offering obviously key insights into early galaxy formation, the nature of dark matter, and of course the transition from the cosmic dark ages to the era of reionization. So, you know, very, very important discovery. It's not confirmed. We shouldn't get too excited about it until it is, but we could have just seen the universe's very first stars. And that, I think, is quite a thought. Any thoughts about that, guys? No? Okay.
Well, we seem to be looking back further and further almost every week or month. We've seen the earliest galaxy, earliest star, and we believe that there is a hard wall there, right? The epoch of recombination, or whenever that happened.
Yeah.
But could we not see,
right?
Could we not see beyond that with gravitational waves?
Yes, because the whole thing about gravitational waves is that it's not electromagnetic radiation.
Right.
It's waves in space-time itself. So, you know, we know that we can't see optically or with any other EM radiation back further than 380,000 years after the Big Bang. But gravitational waves are thought to have been emanating, if you like, from the birth of the universe, and they don't have that restriction because they are ripples in space-time itself. Unfortunately, they are going to be very, very, very low frequency. And I read an estimate somewhere that said they're so low frequency that one of those gravitational waves may pass through the Earth every 100 years. So, you know, they've got such a long wavelength, but they should still be detectable, and quite they have a fingerprint that will identify them as such. So when LISA is launched in 2034, I think it's currently scheduled for, the space-based laser interferometer, that should be able to detect these so-called primordial gravitational waves. So we've got that to look forward to. But you think what primordial gravitational waves could tell us? In fact, it's the only way one can conceive of whereby we can observe the actual beginning of the universe. So, and the information those waves carry will tell us so much. So we'll all look forward to the launch of LISA in 2034. Okay, now moving on, just one final news item. Don't know whether we've heard of brown dwarfs, but have you heard of black dwarfs? Probably not. Okay, so what's a black dwarf?
No.
Well, some recent theoretical work proposes that in the galactic center there could be dense clouds of dark matter. Okay, and these could power a new class of substellar bodies called dark dwarfs. Unlike ordinary brown dwarfs, though, these objects will be heated largely by dark matter annihilation rather than hydrogen fusion. So what happens is in regions of high dark matter density, particles and their antiparticles may self-annihilate when captured inside a substellar object like a brown dwarf, converting their mass into heating energy. In the model, a dark matter-rich environment near the core of the Milky Way provides the required capture and annihilation rates. Now, how would you tell one of these dark dwarfs from a brown dwarf? Well, they would differ in mass, temperature, luminosity, and chemical signature, but most notably, they would preserve higher abundances of lithium-7, which brown dwarfs normally away. So it's this overabundance of lithium-7 which could theoretically be used to detect them. Detecting a population of dark dwarfs would offer a unique and indirect method for obviously probing the particle nature of dark matter, supporting the paradigm of heavy self-interacting dark matter candidates such as the famous WIMPs, the weakly interactive massive particles. So basically, if we look for brown dwarfs in the galactic center and they have an overabundance of lithium-7, then that's what they could be. They could be fingerprints of dark matter. So I thought that was quite interesting idea. I'm not enough of an expert to say whether it carries any weight, but I guess we just have to find things that look like brown dwarfs at the galactic center, and see what happens. So there we are. So there's the news for this week. Hope you enjoyed that. And now what we're going to do is we're going to go straight over, of course, to Dave, who is, as I said, has been sort of adopted as our Space Oddities historian. So Dave, what have you got on this day? What's been going on? What was going on?
Okay, so let's see. I guess you have my presentation, or
sorry. No, don't see it.
Okay, all right, then you're gonna have to give me a second.
Yeah.
Okay.
You'll have to, Dave. He's quite new to Space Oddities, so
I'm sorry. No.
There's no need to apologize. There's no need to apologize.
He's making the mistakes we all made last week.
No, I thought I uploaded it, but I guess I didn't know quite how this worked. Okay, so let me see. November 25th. That's today, right? Okay, here we go. And then I need to. I don't want to ask the AI assistant anything. And I guess I just need to share my screen. Okay.
Right.
All right. Share your screen. Yes. And share this window.
This is insanely valuable on-air time.
I'm sorry. I know. I'm waiting. People are leaving.
There we go.
I'm really sorry about that. I've ruined everything. I've ruined the whole thing.
Don't worry.
So, all right. So November 25th. So yeah, I mean, it was an interesting day. 92 years ago, the Soviet Union, this group called GERD, which is basically, I guess you'd probably say the equivalent of the Soviet Union Jet Propulsion Laboratory, the group to investigate reactive devices, I guess is the best translation. They launched the GERD-10, which was actually wasn't their 10th attempt, but I won't get into that. But it was the first liquid-fueled rocket launched by the Soviet Union, about 7.5 years after Robert Goddard launched his liquid-fueled rocket in the United States. And they were experimenting with all sorts of combinations of gasoline and alcohol and various other propellants, and for at least a few years we're using high pressure oxygen streams, and finally got to a working model with liquid oxygen. The engine failed at about 80 meters height altitude, but it was a some semi-successful launch, and it was the first one, as I said, that ever took place in the Soviet Union. So it was quite an accomplishment for them. They also had this, which was a pretty big advance already, and we're only talking about a few years of time with these liquid rockets, is using liquid oxygen as a coolant, because of course the combustion chambers would and the nozzles would get so hot, and so what they did was they actually circulated the liquid oxygen around the combustion chamber and the upper part of the nozzle rather, before they dumped it into the propellant, basically into the combustion chamber to cause the thing. So they used the actual fact that the liquid oxygen was so cold to keep the combustion chamber from overheating. And of course, that was one of the big problems with early rocketry, and still is a problem, I guess. Is it just generates such an incredible amount of heat. There aren't many substances that can withstand that kind of heat. So cooling is actually a pretty critical part of actually launching any kind of a rocket. And they were one of the first groups to come up with this idea. But anyway, they obviously they went on from there, although they hit some big setbacks because basically Stalin sent a lot of the best, like Korolev, and a lot of their top designers and engineers and scientists to various concentration camps in Siberia, and so basically cut short their rocket program for quite a few years. And although after World War II ended and a lot of these people got back to work on it, obviously the Soviet Union, Sputnik and Luna missions and Yuri Gagarin, they made up the time. They made up the time and actually pretty much, with the help of some of the German rocketry people that they got hold of, they did sort of surpass the United States, at least for a while. So yeah. I mean, so anyway, it's interesting, but here you go. They were, maybe, I guess you could say they were 7.5 years behind us at that point, but caught up. In any case, and then just 20 years ago, a Hayabusa spacecraft, and if you remember, a Japanese spacecraft, it went to the asteroid Itokawa. The idea was to collect samples. It had a little, basically a horn kind of collector thing that it would set down on the asteroid, and then it was supposed to shoot a projectile into the asteroid at 200 to 300 meters per second, something like that, and knock off pieces of the asteroid. Of course, with such a low gravity, microgravity on the asteroid, it wouldn't take much anyway to shoot a lot of pieces up into the air, and they basically would go up into this horn and kind of, well, they had like a tube. It just went around the corner of the tube and went into the sample collection chamber. Unfortunately, apparently, as far as they could tell, the projectile never worked. This was their second attempt to try to collect the samples, and as far as they know, it did not work. However, but they still did close up their sample chamber and send it back to Earth, and it did have some tiny dust particles in the chamber. There's something, I can't remember, 40, 50 particles, but certainly enough to do a lot of analysis, which is the nice advantage about sampling, because you bring it back to Earth, you have a machine that takes up half a building, to look at your samples. Obviously, you can't take that into space, and it's amazing what they can do in situ in space. But there's nothing that compares to having actual sample on Earth and bring it back with you. So that's anyway, it was a pretty big advance. Every asteroid sample that we get back here is an amazing addition to our knowledge of the solar system, and so this was a pretty big deal. No telling when these particles got in there, the first or second sampling run, but probably just when it touched down, because of the microgravity, just the sort of impact, even if it was a very slow impact on the surface, knocked up enough little dust particles that some of them sort of floated into the sample collection chamber, and it worked. So that's what I've got. That's for today. I guess I will say tomorrow, if this meeting was on November 26th, 60 years ago tomorrow France became only the third country besides the United States and the USSR, obviously, to put a satellite in orbit around the Earth. So, and yeah,
Wow.
that's it. That's what I've
I
got.
can't believe Hayabusa was 20 years ago. I mean, that's just Dave,
I agree.
Dave, I'd love you to keep doing these on this day. They're brilliant, but
I'd love
on the
to.
other hand,
No, it's great.
on the
fun.
other hand, they're making me feel very old. So,
Yes.
so there we are. Okay, so thank you very much, Dave. So if you could,
Sure.
stop sharing, and we will move on.
Okay.
Thank you. Great.
There you go.
All
You got it back. Okay.
So there we are. Yeah, you know, it's great because we tend to forget these things, and you know, it's incredible to think that only 92 years ago they were just learning the basics of liquid fueled rocketry, and Stalin notwithstanding. And,
I was telling my wife that, right? I mentioned that to my wife. I said, yeah, it was, you know, the Soviet Union, which were 7.5 years behind the United States. And she said, well, when did the Wright brothers fly? And I was like, oh, yeah, that was only a few years before. That was 1903, right? So
that's right.
Yeah,
we're only talking about a few years before we're building rockets. That's pretty
Well,
unbelievable.
so in 92 years, we've come from those, you know, what we would call primitive experiments to sending spacecraft beyond the solar system.
Exactly. Right. So it's
So there we are. Ian, the CAD, says, thanks, Dave. Love the way you make Andy feel old and give us info at the same time. So yeah, thanks for that, Ian. Yeah. Any more of that behaviour, I'll set Michael on you. So.
Hey.
So anyway, so there we are. Okay, well, let's move on. So what we're going to do now is to have a look at new observations of a very, very, very interesting and quite incredible black hole system. So just give me a second to sort myself out here, and I will share this with you. Okay, so here we go. So what's this all about? Well, this is a system which has the wonderful name of OJ287, and this system has been known about for quite a considerable time. In fact, more than 130 years we've been observing this system. So what is this all about? Well, first of all, let's have a definition of what OJ287 is. So this is a blazar located about 3.5 billion light years away in the constellation of Cancer. This extraordinary system hosts 2 supermassive black holes locked in a gravitational embrace, making it one of the best studied binary supermassive black hole systems in the universe. And we don't have that many examples of binary supermassive black hole systems. Now, if you're wondering what a blazar is, if you don't know, it's an active galactic nucleus where the jet from one of the supermassive black holes is pointing right at the Earth. So we're looking right down the jet, if you like. And that's what a blazar is. You can see from the illustration here. So we're looking right down the jet, in this case from the primary black hole. And as I said, we've been observing it for more than 130 years. And what happens with this, that every 12 years, we see flares coming from this system optically. So the whole system gets brighter with these flares. And the flares occur roughly, but not always, a year apart. So we go for 12 years, and then we get 2 flares, which we can see optically a year apart. What is going on? Well, what's going on is that the primary black hole, which now there's a bit of debate about this at the moment. Earlier estimates put it at 18 billion solar masses, but new studies have suggested it may be as, inverted commas, little as 100 million. So there's a big discrepancy there, which hopefully is going to be resolved with future observations. But it has a massive accretion disk surrounding it. The secondary black hole orbits in a way that takes it through the accretion disk every 12 years. And when it enters at one side of the disk, we see a flare. And then, as you can see in the diagram, when it goes, if you like, under the accretion disk on the other side, we see another flare. The secondary black hole, they're fairly sure, has a mass of about 100 million solar masses. And you can see the scale of the thing here. That's 10 light weeks shown at the bottom here, which is, you know, a gigantic system. So this is how the system works. So that the elliptical path of the secondary black hole brings it dangerously close to the primary black hole twice per orbit. And it plunges through the accretion disk twice per orbit, although not always, and we'll come to that, creating this sort of characteristic double optical outburst, which makes this a unique system. So here's an animation showing exactly how this all works. You can see the secondary black hole plunging through the accretion disk and then out the other side a year later, on both occasions causing flares. Well, the smaller black hole's passage through the accretion disk produces bursts of radiation by disturbing this accretion material. International campaigns spanning radio to gamma rays right across the spectrum have confirmed jet activity and complex interactions within the sort of the core region. Long-term monitoring and sophisticated modeling have refined orbital parameters and black hole mass estimates with increasing precision. So we're getting closer and closer to working out what this system is all about. But in recent years, there have been some incredible advances in our understanding, thanks to new observational campaigns and obviously new analytical techniques, new technology. And Professor Stephanie Comassa, employed over 14 frequency bands to study the core of this system in unprecedented detail, revealing complex spectral behavior. As I said, the new calculations that she's done suggest the primary may only be 100 million solar masses. But there's a lot of debate about that. They've used X-ray spectroscopy from SWIFT and XRT observations to refine the secondary's mass, this figure about 150 million solar masses. And they found that there is jet activity, not just from the primary with that blazar with the jet pointing straight at the Earth, but also there's jet activity from the secondary black hole. And for the first time, we have an incredible image of it. And this is it. This is the jet from that secondary supermassive black hole shown on the left. Now, one thing that should immediately stand out about this jet is that whereas jets are normally straight die, this one is really, really twisted. And why is that? Well, first of all, let's talk about the image itself. Back in 2016, the Russians had a radio telescope in space called Radio Astron, and although it's defunct now, and it only operated for a few years, what they did was they linked it to a ground-based radio telescope network. Now, I've talked about VLBI, very long baseline interferometry, before, but basically, if you have a long distance between the telescopes on the ground and the satellite, and they're making exactly the same observations at exactly the same time of the same object, you can get much higher resolution. And that sort of imaginary line between the two is called the baseline. So with longer baselines, longer distances between the telescopes that are linked together, you can get much higher resolution. And this has enabled them to take this amazing image. So why is it all twisted? Well, as you might expect, this is due to interactions with the accretion disk around the primary. Every time it passes through it, this jet sort of gets warped and twisted out of shape. We don't know the exact physics for that, about what's going on, but the fact that we have this image at all is absolutely stunning. Remember, you're looking at a system that is 3.5 billion light years away. So obviously you're seeing it as it was. Who's rustling papers? you're looking at as it was 3.5 billion years ago. So this image really is an incredible achievement. It's taken since 2016 to analyze the data, believe it or not, to come up with this image. So although the image was taken in 2016, it's only really been produced now thanks to new analytical techniques and new technology. Now, if we look at an edge-on view of the system, on the left there, you can see we're looking at the disk edge-on, and you can see the secondary black hole precessing around the primary black hole. And you see the dates on the right, and every time it does so, you see 2 peaks. But you don't always see 2 peaks. If you look at the next one, we see 3 peaks. And that is because of that orbit going rapidly in and out of the disk as it gets closer and closer to the primary. So the number of flares varies, and the actual gap between them varies depending on that sort of flower-like precession of the orbit of the secondary around the primary on the left-hand side. So, this goes back to 1899, these observations. So we have been observing it since 1899, and these optical flares have been observed every 12 years since 1899. So we can now make very accurate predictions about when we will see them again. The last flares were seen in 2023, so we got about another 10 years before we see more optical flares from this system. And the great thing about this is a natural laboratory for the testing of general relativity. And especially where, as we know, the best place to test any scientific theory is in extreme conditions to see if it breaks. The timing of these outbursts matches predictions including relativistic precession and gravitational wave emission effects with remarkable accuracy. Now, because of the emission of gravitational waves, the gravitational waves are sapping energy out of the system, meaning that the orbit around of the secondary around the primary is getting smaller. And therefore, the secondary is getting closer to the primary. And they will one day merge. And this is expected to be in about 10,000 years. So we've got another 10,000 years of observing this system before the 2 black holes merge. Although, of course, you must remember, this has already happened. It happened 3.5 billion years ago. But we won't see it happen, the merging of these black holes, for another 10,000 years. What will happen during that time is that as the 2 black holes get closer, the amplitude of the gravitational waves will get bigger. So we'll get bigger gravitational wave signals as the 2 black holes slowly come together because of the draining of energy away from the system by gravitational waves. So although we don't have the technology to detect these waves yet because they are very long wavelength, again, when LISA is launched in 2034, we may be able to detect these gravitational waves, which will only get stronger as time goes by. So predictions for future behavior, well, you may say, well, so what? We know what's going to happen in the future, but what does all this mean? Well, what it means is very simple. This system is a rare insight into binary black hole evolution. As I said, we haven't got many examples of binary black hole systems. And this is, fairly cosmically nearby, 3.5 billion light years away. So this is a key phase in black hole mergers. And of course, also it says a lot about galactic evolution, because we know that supermassive black holes affect the evolution of their host galaxies, something that we've really only appreciated within the last decade or so, that supermassive black holes are crucial to the evolution of galaxies and indeed control their evolution by their radiation suppressing the formation of stars and so on. So this is a great system to study, to see how galaxies actually evolve and what phases they go through. It's an extreme physics laboratory to help us understand relativity under extreme conditions, gravity under extreme conditions, jet formation mechanisms in the most violent environments. And of course, we're testing fundamental physics all the time. This is a cosmic clock, after all, which we can use to test general relativity, gravitational emission, and black hole spin effects with unprecedented precision. So there you are. So that is the black hole system OJ287. I find this system absolutely fascinating because we haven't got another system like it to study. It's very lucky that we've been making observations for 130 years, slowly learning more about this this system. So there we are. Okay, so any thoughts about that, guys? No. Okay. Right. Fair enough then. We'll move on. And what we're going to do now, of course, is to go over to the man with his finger on the pulse of the night sky, or something like that. We're going to go over to Roger, who's going to tell us what's up in the night sky at the moment in November. So, Roger, take it away.
Okay, so we're now coming up through the end of November into the 1st of December. Oh dear.
Oh God, yeah.
I know. So what's going to be happening over the last week of November, we all ask. So at the moment, as some people might have seen this evening, a lovely waxing crescent moon out there, leading up through the phases of the first quarter, coming out at the weekend. So all good there. And if we look at the night sky, this is for the 10th or 10 o'clock at night. So as you can see, we are still got Saturn over on the western horizon. And we've also got Jupiter coming up nicely. But we can see over in the southeast a lovely constellation called Orion coming up through. And winter is now coming, so things are all looking rather nice now for us astrophotographers, although we still have the dominating Andromeda galaxy almost overhead, which is just as good. Okay, but before sunrise, although this is some time after sunrise, we've also got Mercury and Venus coming up through. And following onwards, quite closely behind is Mars. But just behind that also is Comet Lemon, but that's becoming too much of a problem to see now while it's after sunset. So I'm afraid I think we've pretty much seen the last of Lemon for any practical observations. But there are other comets about, as we are all aware.
Yeah, there are.
So we've got Jupiter, Saturn, Uranus and Neptune visible in the night skies. Obviously, Uranus and Neptune will need somewhat more of than the naked eye to get an appreciation of it, but they are visible with binoculars or a small scope, and you will see some coloration there as well. So let's have a good look at that. And we're almost back up to an edge on the Saturn rings again. But they're just almost, not quite close, but very, very close. So an interesting time to see any transiting moons going across the disk. So keep an eye out for that. We do have some which will be coming across, obviously with the Jupiter as well, which are all quite interesting. We have got images and photographs from our gallery subscribers. And talking of gallery subscribers, here are this week's entries for us to admire. Now we've got one from Lee of the Owl cluster with his C-Star S50. And this was in Cassiopeia and discovered by William Herschel, no less. Now this is only a open cluster, but
nice.
a very nice cluster as well.
Yeah.
Lovely colours of the stars as well. Well done, Lee. You do produce some rather outstanding images. And when he's finished with that one, he's got the Caroline Rose cluster. This is in honour of William's sister, who did rather a lot of observations herself. Now, this is about 8,000 light years ago away and about 1.6 billion years old, according to this. And this is only 33 minutes of 20 seconds exposures. And this is the resulting image. Wow.
Very nice.
Interesting little cluster.
Yeah. Yeah. It's quite dense in the Milky Way, isn't it?
It is, yeah. If it was any denser, it'd be a globular cluster.
Yeah, I was going to say, it's definitely not an open cluster, is it?
No. So we're back to Jerry, and he's got the Pleiades with his 4-inch Esprit. No filters, and 880 seconds times 60. Right. And we've got some lovely,
Jerry.
lovely gassy colours there.
That's
beautiful. Look at that nebulosity, the detail in it. It's amazing. With a 4-inch telescope.
Yep.
Wow. Wow, that is truly amazing.
Well done.
Well done, Jerry. Another winner.
And we've got an interesting one here from Kenneth, M31. And this was with his Olympus Micro Four Thirds camera with 100 to 400 mil lens. And this is 90 minutes.
Wow. That's
nice.
beautiful.
Very nice.
I like that. That's lovely. Captures all its glory perfectly, doesn't it?
Yeah, he's find that he seems to get better images with his Olympus camera than some of his Astro gear. So he's been selling some of his Astro gear because it's not producing the same quality results as his Olympus. So there we are, you know.
Yeah. So interesting comment from Barry. I think we all feel this, Barry. Winter may be the best time to stargaze, but my body tells me otherwise.
Yeah, absolutely.
Yeah, we know exactly what you're saying, Barry.
Yeah, frozen to the bone.
Absolutely. It's sort of when you make a decision in your life to become an armchair astronomer rather than an actual.
Yep.
Go out and get your nuts frozen off.
Right. Well, we've got some images from a new subscriber here, Stuart Gregory, and he's also done the Pleiades with his Sea Star, and that was taken on the 17th of November. And he's managed to capture some of the gas there as well.
That's
very nice.
Beautiful, isn't it? That's a Sea Star. Amazing.
That's what. Yep.
That's amazing, Stuart. That's so beautiful. It's a real Christmassy image, isn't it?
Very.
Yeah. Lovely. Well done indeed.
And then he's managed to produce this image. Any constructive criticism welcome. And this is the Orion Nebula.
Oh, that's dreadful. That's absolutely dreadful.
Wow.
Very nice.
That's beautiful.
We need to get some definition in the trapezium there, so we need some shorter exposures as well to go with that, because it's very tricky because it's so bright. You can blow out the area around the trapezium, but you're almost there with it, and we can also see the Running Man there as well.
What integration time is
Oh
this?
yeah.
Let me just go back. So we haven't got any any time with it, but
that's nice.
So
I wouldn't have thought it would have been more than an hour or so.
No.
But it's a very good start. Very good.
It's excellent. It's excellent.
Yeah. And finally, we've got this one, which is, we shall see. Another one of M31, the Andromeda Galaxy. Yeah.
You've done well, Stuart. That's brilliant.
Lots of
Yes,
gas.
he's getting the hang of it. You can start to see the dust lanes coming up quite nicely with that.
Yeah, absolutely.
Hmm.
Definitely.
Hmm.
Wow.
In fact, I did see one YouTuber in America, Trex Astrophotography, was doing a comparison of some images that he did of the Andromeda Galaxy, and he spotted some new stars in there. Doing a comparison of between two images, between one that he'd taken last night and one about a month ago. He noticed that there was almost like a double star, new double star in the area as well. So interesting. So there's been nothing confirmed. Right. Okay. Here's my attempt, although not very good, of the Sol Nebula in a Hubble palette.
Roger.
The colors aren't quite right. I'm still trying to work out how to process the sulfur, hydrogen, and oxygen, but I don't have PixInsight. I just use AstroPixel processor. So I sort of comparing my images with what's on the web and trying to adjust the colors to it, and I've got this result. So there we go. Anyway, it's 3 hours of each filter, so it's about 9 hours integration time with that.
Yikes.
But it's quite yeah. If you notice the little nebula part, which is at the 1 o'clock position, just away from the main body, it looks like a bow shock wave there. If you can see that. Yeah,
definitely.
Interesting.
Amazing. Well done, Roger. That's great.
Okay. And here's one I took with my C11 of Jupiter and Io. It's a little bit darker stuff, but you can see Io over on the other side. The seeing wasn't very good. It was a bit wibbly wobbly, but I tried to adjust it. It looks a bit dark, but it gives you some of the idea, the surface details from it. So it's okay.
That's great. Yeah.
And we've got one from down under while Michael's still photographing the sun in Victoria, Australia. And this is just a few days ago. And a nice spotty sun.
It's upside down.
Well, it's one way or the other. I'm not quite sure.
That's well done.
But
that's
he's
brilliant.
still producing good results from down under. Right. Yeah. So these are what I've done today, which is in white light, calcium, and hydrogen alpha of the sun.
Oh.
Wow, that's lovely.
Now the hydrogen alpha one is trying to get the prominence that's halfway across the surface on the edge there, because it looked quite interesting.
Pretty.
I did.
Yeah.
I would have done more of it, but it disappeared behind the trees, so I was a bit snookered otherwise. But there we go.
How very inconvenient of it.
I know.
Yeah.
But that's what the sun was looking like today. And this evening around tea time, I managed to get the moon as well this evening, which I haven't done for a little while, needing my fix. And that's what the current phase of the moon was as of today.
Very nice.
We had that beautiful moon here earlier, but it's clouded out now, needless to say.
That's what you would have seen if you had a telescope out. And that's what we have for this week.
Thank you so much, Roger. That's absolutely brilliant. So, well, if you're new here, by the way, can I just say hi to, we seem to have quite a lot of new people joining us tonight. You are very welcome to Space Oddities. We hope that you will stay around and watch us each week and consider subscribing to the channel and get notified of when we're going live. We post lots of videos on our channel as well. We have over 600 videos about all aspects of astronomy, space exploration, anything to do with the universe. You will find on our channel lots of playlists there for you to have a browse through. So you are all very welcome, and we hope you will keep watching us. And if you could just the favor, which only takes a second, just click the like button if you like what you see, and help us that way, because it really does help us. And leave a comment as well, which equally helps us. So there we are. So you're all very welcome. So what we're going to do now is we'll just say, as normal, if you would like to include your image in our weekly gallery, couldn't be simpler. Just attach the image to an email, mail it to gallery@spaceoddities.space. That's gallery@spaceoddities.space. And we will include it in our weekly gallery. And not only that, you get your own little gallery of just your photos on our website, which is https://spaceoddities.space. And you'll see all the viewers' galleries there with all their images. And we're accumulating, I think we've got about 100 on there now, Roger, if I remember rightly. So we got a lot of images that have been submitted by our viewers with all the details. So you can have a look through those, and we hope you enjoy doing so. So we come to that time of the week when we take a snorkeling trip underneath the clear waters of sanity into the dark, insane depths below, and that being, of course, Einstein of the week, our regular look at some of the insanity going around social media concerning the universe. So please just give me 1 second, and we will have a look at this week's Einstein of the week. Now, I was saying to Roger and Michael earlier, before we came on air, that we regularly see absolutely insane stuff going on social media. This week, I think the crazy people have actually excelled themselves. I can't remember a week when there's been so much outright insanity on the internet. Perhaps it's Christmas is coming and people are getting crazy. I have no idea. But a lot of people really need to have a visit from the men in white coats, as you will see. So first of all, a question for you. Guess who said this? Mysterious interstellar object may be releasing sentinels around Jupiter. Any guesses? Nobody? Oh, come on, you must know who this is. Does nobody want to say his name? Is he the name that shall not be spoken?
Is that the pillow guy?
Not my pillow guy. No.
My pillow guy.
What's happened to him recently? He's made bankrupt. I know, but I don't know. Anyway, now this is Abbey Loeb.
Oh, that's Abbey Loeb. I'm going to say either that or the angry astronaut.
No, not even the angry astronaut. No, this is Abbey Loeb again, now saying that the aliens are interested in Jupiter and they're going to release satellites to orbit Jupiter, which we should be able to detect. No, we shouldn't, Abby. Shut up. So we go from that to something that is pure unadulterated craziness. So just to give this some context before I show this to you, there's this weird idea going round among flat earthers that the moon is a light in the sky generated by a plasma field. And this guy thinks he's found where the plasma field is coming from. While hiking in the woods, I located one of the lunar plasma concentrators in northern Michigan, about 45 miles east-northeast of Escanaba. One of 17 dating to the origins of the world itself. These devices have helped steer and power the plasma field that lights the sky every night.
Well, we now have one of the preeminent world experts on the moon right here on Space Oddities. So, Dave, take it away.
Is that right?
On the spot, why don't you?
Well, I can neither confirm or deny. You know what, Lou? I don't even know where to start. So
No.
Nor do the rest of it.
No, to me it just looks like a TV antenna, but it obviously can't be because it's been around since the beginning of the world. So
yeah, right.
Yeah. So there we are. So Bill Pittman. Well, what can one say? I'm not going to say anything. Okay, now we move on to the Aurora. So, we know what causes the aurora. We know it's the interaction of the Earth's magnetic field with the solar wind. Apparently it's not. You've got it all wrong. I tend to agree with you, brother. Either HARP or just to tell you what HARP is, HAARP, if you haven't come across this is the conspiracy theory that either NASA or the military or both are controlling the weather through secret technology. Anyway, the aurora, it's not caused by pole shifts, as we know what the Word of God says about the description of Earth. And we also know it has nothing to do with the NASA lies about solar flares, as we know the sun is only a light and not some big dwarf of a planetary round object called a huge star by those that deceive the masses. The Word of God and a sound mind that God gives us always helps to come to truth. Thank you, Jesus. So there we are. But I'm afraid it doesn't stop there, because from what causes the aurora 1, we move on to what causes the aurora 2. And this was something else. This lady has a really convincing idea about what the aurora actually is. I think the northern lights are a reflection of the colors around God's throne. The Bible does say gods sit above the circle of the earth. Anyway, it's what I believe personally. Blessings. So now you know. Yeah, it's those lovely colored lights around God's throne. Oh, bless.
All that research down the drain.
Yeah, absolutely.
That's too bad.
So then we move on to what causes the aurora 3.
Wait, stop. I can't take any more. Stop.
I told you this was an extreme week.
This is painful. This is painful. Go ahead.
So what caused the aurora? What it is Project Bluebeam. Just to remind you what I said earlier, Project Bluebeam is this insane conspiracy theory that NASA and or the military or both are going to fake the second coming of Jesus. Why, I couldn't tell you, but that's what they think, and it's called Project Bluebeam for some reason. This mission this plan to fake the second coming of Jesus. But somebody actually said, maybe, but consider this. You've seen what that sphere in Las Vegas can do, right? Now think about how many of those satellite trains have been sent up above us. They're reflective, not lights. Maybe they've built something like that sphere above us. Just a thought, but it can certainly explain how the whole world is seeing these northern lights. Well, obviously the whole world doesn't see the northern lights, but there we are. So the Las Vegas sphere is just being replicated on a huge scale around the Earth by who knows, and who paid for it.
I don't think NASA is going to have enough money left to do something of this magnitude.
No,
that's the proof right there.
Yeah. So there we are. There we are. That's Einstein of the Week for this week. I feel sort of unclean now. I need to go and have a good shower, I think. But I do this for you guys, for your entertainment and edification. So you should have some pity on me, because I put myself through this every week, and you just have to hope at the end of the day it doesn't send me crazy, because if I do it long enough, I swear it will. So there we are.
Pity is not the right word, Andy. Not even close.
Yeah. So there we are.
Wow.
Okay, so there we have Einstein of the Week, and we'll be back, I'm sure, with more insanity next week. So just to finish off tonight, what we're going to do is go over to Michael, who's going to give us our constellation of the week. I hope.
You bear with me.
Of course, we will bear with you.
I need to share my screen all the time. Oh dear. I'll get there in a minute.
Any problems, Michael?
Can you see that?
No. Can't see anything. Bear with him a while. He's got new glasses on today. That might explain it. There we are. Okay.
Hey. Right. Good evening, everybody. Sorry for the long wait for my presentation. Right. Tonight we're going to talk about Cepheus, the king of the northern sky, an ancient constellation that has captivated Cepheus stargazers for millennia. Most distinctive patterns in the northern celestial sphere, from its mythological origins to its revolutionary contributions to modern astronomy. This regal constellation continues to inspire wonder and scientific discovery. Named after Cepheus, king of the Athenian mythology, tells the tale of divine punishments and cosmic redemption. The story begins with his wife Cassiopeia's, which angered the sea god Poseidon. The consequence was severe. A sea monster. The hero Perseus could save her. Moved by the families, Zeus immortalized them all as constellations forever circling the northern sky in an eternal celestial procession.
Oh,
okay.
Yes.
So this is where Cepheus is the concept.
So Michael's mic appears to be cutting out. Michael, your mic appears to be cutting out intermittently, but keep going anyway. We'll see how it goes.
Yeah. Can you hear me?
Yeah, but it does for some reason your mic. Yeah, we can hear you now. I'm just wondering.
I don't know what's that then. So
well, let's carry on for a bit, and we'll see how we go.
Right. So Cepheus borders Ursa Minor and Cassiopeia also, but the Alpha Cephi is known as Alder, which is the brightest star. Same.
Right, Michael, it's cutting out really badly now. Michael, it's cutting out really badly now. So what I suggest you do, can we try again next week?
Yeah, can do. Yeah. I did have a notice on to say that my lost.
Oh, right.
And restart.
Well, if you'd be good enough to try again next week, I think that's probably the best thing to do, because we couldn't really hear what you were saying that clearly. I think he's gone. Oh, he's still with us. Okay. So sorry, viewers.
I'm here.
Oh yes, you are definitely there. I can see you. Yes, it's not a mirage.
Yes.
Yeah, sorry about that, Michael.
The studio software said connection is lost.
Right. Okay. So you've got some sort of connection issue. Ian, the CAD, again says Cepheus rather large for Michael. Maybe that's why it's cutting out. So yeah, perhaps. If you don't know, viewers, it's a sort of an ongoing gag that when we do Constellation, Roger does the big constellation and Michael does the absolutely minuscule constellations. So there we are. You can read into that what you will. So there we are. And Derek Abbott says Norman Collier. Yeah, it's definitely Norman Collier. Definitely. So thank you, Derek. Okay, right. So that's it. We'll revisit that next week. So we're going to draw things to a close for this evening. Obviously, I'd like to thank all the team for being here, Michael and Roger and Dave and Lou. Thanks for your contributions, guys. If you're new to Space Oddities, as I said, just do us a favor, hit the like button. Considering subscribing to the channel only takes one click. It's perfectly free, and switch the notification icon so that you get notified of when our videos and live streams are published on the channel. We've loved having you here this evening, new viewers, and we hope you will stick with us and come back and watch the live stream next week. And talking of next week, we will be back, of course, at the same time, 8 p.m. UK, next Tuesday, when we will do even more funky stuff about the universe. And we hope you will join us for that. So
3 p.m. US East Coast.
Yeah, 3 p.m. Yeah. But
noon if you're in the
Oh,
West Coast.
right. Noon West.
This is going to get so confusing now.
Kamchatka, it's 4 a.m. in Kamchatka.
But let's just say, in proper money, it's 8 p.m. UK. So there we are. So anyway, have a fantastic week, everybody. Stay safe, look after each other. Hope the weather is not too bad where you are. And stay safe, and we'll see you again next week on Space Oddities. Thank you for being here, Sopham.